he likes to tell a story that they would throw ping pong balls in front of the radar dish and they would vaporize.
Wow.
They were transmitting a lot of power.
Hey everybody, welcome to the Pulse podcast from Wavetronix, where we talk about everything traffic, everything transportation, and today we're talking about everything to do with radar and maybe how that plays in with transportation and traffic. Our guest today graduated from Brigham Young University with a Bachelors and Masters in electrical engineering. His master's thesis was on compact antennas for Unmanned Aerial Systems. He's worked in the traffic industry and Wavetronix for a dozen years. So welcome, James Eck. Thank you for being here.
Hey, thank you for having me, Todd.
My introduction to you was in a class where you were talking all about radar. So This is fitting. Tell me, what is radar? For the layman out there, what is radar? Because everybody knows it's out there. Maybe planes have it. Maybe there's a cop with a radar gun, but it's really everywhere, isn't it?
Yeah, well, so fundamentally radar is using radio frequency waves. Right? I guess it's an acronym. We could start with that. And it's a dumb acronym because engineers like dumb acronyms. And so the R and the A both go into radio. And then the important thing is detection and ranging, right? So you're using radio frequency waves to detect things and get their distance from the radar. And that primarily happens because when you transmit a radio wave, it bounces off of most things. Anything that's conductive at all, it will bounce off of people, water, wires, anything metal.
And it'll bounce differently depending on size of object, distance.
Yeah. Yep. And so depending on the wavelength, some things look larger. It's actually relative to the wavelength, how big the thing looks on radar. And the shape matters a lot too. So like you could have a metal sheet that is directly toward the radar, that basically looks like the size that it is, right? But if it's turned at an angle, that looks like a very different size, right? And then if it's maybe a metal sphere, how big that looks depends a lot on the wavelength. And so there's a lot of different factors that go into how reflective something is for the radar bouncing off of it.
So the science of radar, radio waves, was that an accidental discovery years ago, or how did that play out?
It was theorized by James Maxwell, in the 1800s. And James Maxwell was actually pulling together the theories of a lot of different people. You had Volta and Ohm and Ampere had all created the laws that maybe you've heard of, Ohm's law and Ampere's law and volts are a unit that we all use, right? And so all these guys had done lots of experiments and determined a lot of things about how electricity works and how magnetism works and how they kind of interacted with each other. And Maxwell brought it all together and created what we call Maxwell's equations. The Maxwell's equations that I learned in college and that anyone learns today are really 4 equations that were developed by Heaviside years later, but we still call them Maxwell's equations because Maxwell developed them first. But his equations were 13 equations. It was much more complicated. Heaviside really simplified it. It doesn't get enough credit. Nobody knows Heaviside's name.
It's a great name.
Hopefully now they know Heaviside's name.
Exactly.
And so we use the Heaviside equations, but Maxwell unified in these 13 equations all of the theories that existed at the time from all these other great thinkers and created what we call Maxwell's equations that theorized that electromagnetism, like light and radio waves, behaved like a wave. And so he theorized the existence of these waves. And they were later proven by Hertz because he'd read Maxwell's things and wanted to prove it. And he created an experiment where he created a spark at one end of the room and it appeared on the other end of the room, proving that energy had traveled through, we say the vacuum. He probably didn't have a vacuum, but through the air, like a wave. And he could measure the time between when he created it and when he received it on the other end. And now we know the speed of light, right? And so the discovery of radio waves, I think is what you asked about, was not so accidental, right? It was an intentional progression of trying to figure out what is this thing that sometimes shocks us when we rub our socks on the carpet, and eventually figuring out all the properties of how these waves behave.
So why is radar so important to us today? And how did it develop over the years, the technology?
Sure. my understanding is the first development of radar came during World War II. Leading up to World War II, as a way to detect aircraft from further away. And the story goes that Arnold Wilkins was asked to come up with ways to deal with aircraft, including like a death ray to boil pilots, right? And the power requirements are astronomical. But he recalled a memo that he had seen from the Postal Service that airplanes flying overhead were messing with their radio telegraph signals. And I don't know, did they ever tell you in elementary school that there was a such thing as radio telegraph? You always see the telegraph poles, but radio telegraph, I mean, that's a pretty cool development that just gets skipped over, right? Well, he figured that if the planes were messing with the radio telegraph signals, that meant that the planes were detectable with radio signals, right? And so they perform what we call the Daventry experiment at Daventry Park, where they set up a transmitter and they set up a receiver and they transmit between them just like a radio telegraph would have done and fly an airplane overhead, and they can see the disturbance that the Postal Service was complaining about. And right there you have radio detection, right? The first 3 letters of radar. After that, it was just a matter of knowing the speed of light and the travel time to get the ranging as well.
And in the UK, they developed this because of the war, correct? And really developed quite an elaborate system with towers all along the coast. Yeah,
they call it the chain home network. And so it was to detect, well, they knew that there was a German threat once again, right? After World War I, they'd been bombed during World War I. They saw this coming again, potentially. And so they developed this to be able to detect those incoming planes and be able to scramble their own pilots, but also pilots from all over the world who were flocking to Britain because their countries were taken over by the Third Reich threat.
Yeah. And I mean, I read just the other day where it said the development of radar was more consequential in ending the war than the atomic bomb.
Yeah, well, we definitely have historians who say things like that, right? I can't remember his rank, but there was a Roskell Navy historian in the UK who said that it was the centimetric radar set stood out above all other things for winning the war. That particular type of radar, very short wavelength relative to the wavelengths used in the chain home network, was an airborne radar for detecting submarines to attack them at night, right? Because submarines, well, we didn't call them submarines, U-boats, would come up at night to transmit and report in, right? And the UK had a number of stations in like North Africa and the UK and Iceland that they could use to triangulate the location of these transmitters to know where the U-boats were, but not so precisely, right? So you get there in the airplane ready to take out the U-boat, and it's dark, and they're only doing this at night because it's safe at night. And if you turn your lights on, they can see you and submerge, right? And so they would come in with the radar instead and take them by surprise, right, before they could submerge again. And it really turned around the Battle of Britain, which then allowed England to get the supplies that the U.S. was sending over and start to turn the course of the war. And so you could make that argument, at least in Europe, that it was more effective than the atomic bomb.
And I mean, the nuclear race was a race, but there was also a radar race between nations at the time, weren't there?
I'm not aware of what the development looked like in other countries, but I have heard that in the UK they had propaganda saying that their pilots ate a lot of carrots to explain why they were able to attack at night, to kind of veil the fact that they were doing this radar development. And the radar development was done in very secret labs at MIT and things to avoid getting out into the public, right? It was a guarded secret for sure.
Yeah. Tell me about radar and its impacts on the body. Does radar harm you?
Well, no, not today, but it could. My wife's grandfather was an electrician on a Navy ship in the Pacific during World War II. And he likes to tell a story that they would throw ping pong balls in front of the radar dish and they would vaporize.
Wow.
They were transmitting a lot of power. Today we have lots of limits on how much power you can transmit. There's probably still radars in the world, like if you stood in front of like a NORAD radar, maybe could be damaging. But the frequency that radar works at is not ionizing, right? So when we talk about UV rays causing cancer and skin cancer, right? That's because it's ionizing radiation, right? It creates ions in your cells that then cause the mutations that we know as cancer. And the frequencies we use for radar just simply aren't ionizing radiation. What they can do is warm you up, right? So you could get like a microwave. Right?
Yeah.
So you could start to maybe even get a burn if there's enough power, but they're not going to cause cancer. My dad worked at Motorola, and he tells a story about how they had to do experiments to determine when they were creating cell phones, the first cell phones, they had to determine if it was going to cause people problems holding this device next to their head all the time. And so they taped a bunch of cell phones to the sides of pigs' heads.
Wow. Because
pig brain biology is similar to human, apparently, just to observe if it would have these types of effects, right? And the pigs were fine, right? And so the experiments bear out that we're okay to use these things, right? But yes, with enough power, there were other experiments done where rats could have problems due to the heat generated by very powerful electromagnetic waves.
Oh, and that was a concern. In the U.S., I understand there were reports from Germany that they were developing a death ray out of radio waves, radar. So
yeah, and it could be done. It's just a lot of power to do it.
There wouldn't be enough power
yeah,
to do that sort of thing.
Well, there would be if you were really, really close, right? Like if you put someone in a microwave, then you could have a death ray.
Yeah. So you've mentioned frequency and wavelengths, and explain all of that to me about the science of radar.
Sure. Oh boy.
So this was part of your class, but you had a board and you could, sketch it all out, but kind of just the overview.
Yeah. So as an electromagnetic wave travels through the vacuum or free space or water or whatever medium, the way it does it is that the electromagnetic field, the electric field, is coupled with the magnetic field, and they're always perpendicular to each other. And so they create this coupled oscillation through space. And so when we talk about the frequency, we're talking about how many times per second that field is oscillating from top to bottom. Well, top to bottom to top again, right? And then the amount of space that travels through during that time period of an oscillation, we call the wavelength. And then amplitude is kind of the strength of that oscillation.
And by measuring those, that's how you can detect an airplane or a ship or different things like that, correct?
Primarily by measuring the amplitude.
Yeah.
Is how you would detect that there's something there at all, right? And then to determine how far away, so the detection, part of radio detection and ranging, right, is that you've received some amplitude that tells you, oh, this is above, we call it the noise floor, right? There's a certain amount of noise that's always there, and you can't do anything about it, right? Some of it comes from temperature, some of it comes from other things interfering, some of it comes from inefficiencies in your systems, right? So there's always some noise there. And if you see amplitude that significantly comes above that noise, that's detection. We've found something, right? The ranging comes in by knowing the time delay between when you transmitted the signal and when you received it. And so there's interesting developments there where during World War II and during the early development of radar, you were sending a pulse where you turn it on for a little while and then turn it off again. And then when you received it again, you knew how long it took to go and come back, right? And that's part of why they were transmitting so much power that they would explode ping pong balls.
Yeah.
It's because you can only turn it on for a second, right? And so the more time you have it turned on, we call that the dwell time, the more power you receive back, the easier it is to get it above that noise floor. Well, they had to turn it off and on pretty quickly so that when it came back, they didn't have it on anymore. Otherwise, all you see is your transmit, right? You have to see the thing coming back. And so their dwell times are very short. Our radars at Wavetronix and most modern radars are using more sophisticated methods where, for example, our radar uses FMCW, which stands for Frequency Modulated Continuous Wave. Continuous wave means it's on all the time. You never have to shut it off. And frequency modulated means that we're ramping that frequency up so that when it comes back, this is when I really want the whiteboard, right?
Yeah.
I'm going to do two angles. So you got what you're transmitting now is in the past is in the future relative to what you're getting back, right? What you're getting back is something that you transmitted a while ago. And so it is at a lower frequency than what you're transmitting now, because when you transmitted, it was back when you were at a lower frequency. And so by subtracting those frequencies from each other, we can then figure out what the time difference is between the two, because we know the slope of our line. We know how quickly we're changing the frequency, and that's how we determine the range. I don't even remember the original question.
Me neither, as a matter of fact. But I mean, that brings us to what is happening at Wavetronix. And really, my next question would have been, how prevalent is radar in people's lives? And they have no idea. And Wavetronix is a part of that.
Yeah, radar itself, maybe not super prevalent. Like, people know that policemen have radars, right? And we know that Wavetronix has radars, and maybe there's just lots of other radars I don't know about in my life, right?
Yeah.
But they're being used for airplane navigation and these days car navigation, right? There's a lot of radar being implemented in newer vehicles for collision detection and avoidance and lane keeping and all of these things. So, but maybe I just don't know that people don't know about these things, but I feel like I'm familiar with all.
I think most people know when they watch the weather at night, they're using radar, right? They know about the policeman with the radar gun. I don't think people know that when they roll through an intersection, radar is detecting their vehicles.
Anyone who's driven with me knows, because they say, "Oh, we're being irradiated."
Yeah, you're that traffic geek who geeks out over those things. Like, look, that's a unit up there. You know, I do that with my family too. But that's showing the prevalence, and even something as simple as a microwave. It used to be called radar ranges back in the day when they first came out.
I didn't realize
you didn't know that. Yeah. I'm old. So, I remember hearing that term, and put it in the radar range. It'll get done so much faster. And it was a microwave.
Yeah.
And a microwave is radar, right? That's manipulated.
Yeah. It's not detecting anything, and it's not ranging, so I wouldn't call it radar, but it is electromagnetic waves. It's using the same physics to do what it does.
Okay, makes sense. In this creation of what happens with Wavetronix and vehicle detection, how does radar play into that?
Wavetronix comes onto the scene trying to solve traffic problems, right, in a time when they're cutting loops in the ground where you have to cut one for each lane, right? And for each zone that you want to detect in, you have to have your own loop. And then there's cameras coming onto the scene at the same time, but they're struggling in low light and high light, right? In twilight, right? In the dawn and in the dusk, because they have to change algorithms somewhere in between there, and there's not something good for the crossover point. Weather is a problem. And so Wavetronix comes onto the scene using some of this coming out of BYU, right? David Arnold and Mike Jensen have labs there where they're developing radar with their students and realizing that this can be used to detect vehicles and make these problems a lot easier to solve. And so that's allows Wavetronix to come in and really disrupt the industry, right? Create these devices that are easier to install, perform better in some difficult conditions, and really revolutionize how things were going, right? And come in at the time under price of cameras and things like that, right? Because of how cheap it is to produce printed circuit boards and some of these other, the ICs, the integrated circuits that are used for the processing. But things have changed a lot, right? Radar is a lot more prevalent now. There are a lot of competitors now using radar, and the innovation continues, especially now that vehicles are using radar. The chipsets to achieve radar for traffic detection are very prevalent, right? Everybody's trying to make them because everybody wants to get into that big auto market.
And it's evolved over the years. Started out with just side fire radar, right? Explain to me what that is.
Sure. So the dream, of course, was to do intersections first, but the idea was that maybe that was going to be a little bit too hard. So side fire is that your radar is shining kind of perpendicular to the path of the car. And part of the reason that's a lot easier is that you don't have to worry about a big wide area. You just kind of have this curtain that you're detecting the cars coming through, and so it makes the radar design much simpler. But also cars look much brighter. You remember I talked about the metal sheet. It might be very bright facing toward you, but turned away, it might become invisible because you bounce off and away. Well, the side fire is looking at the cars right on the side, right where they're the brightest. I wish I could put up a plot, but car companies will actually measure their cars on a big turntable, what their radar cross-section is. And so you can see on that plot, right at the side, there's a giant spike that comes out, and then it's all just kind of jiggly all the rest of the way around, and then a big spike on the other side and jiggly around. And so it makes it a lot easier to see the cars on the side, right? And so that, I guess that's the summary of side fires. That it's,
Sure.
First it was the V, and I don't even know how the V got speeds, but somehow it got speeds, black magic. And now we have the HD, and the XP20 followed the HD, right, where we've got two separate beams that the car drives through, and it's got like two curtains, right? So we can say, oh, it took it this long to go the 4.5 inches from one to the other. But it's not quite that simple, because we're saying that we detected how long it took a car to go 4.5 inches from here to here, but that beam out 100 feet away is actually 10 feet wide, right? It's not that narrow of a beam. It's pretty narrow, but 100 feet away, it's now a very wide beam. And so it's really in both beams for almost the whole time, right? It's two 10-foot wide beams with 4.5 inches on each side that are different. And so we do some black magic and math to figure out exactly when it entered each beam. And I don't know if we want to talk more about the algorithm behind that black magic, but it's...
I mean, go for it. And then we want to talk about intersections.
Okay.
And how that evolved.
So we do what's called correlation, right? Where you're getting these returns from this beam and the returns from this beam, and you shift them in time until they match up with each other, right? Is kind of the simplistic way to do it. There's a mathematical function where you determine that determines how well they match, right? But you shift them in time until they match up, and then that's how you know how long it took to go from one to the other. And I guess I didn't really say very much, right? But the actual algorithm, the math that you do to determine that correlation is the black magic that you look at and go, I can't believe this works, but it does.
It does, yeah. And then we got into intersections, and you said that was the dream initially, but it took a while to get there. What were the limitations with radar that needed to be worked through to make that happen?
Sure. Part of it is customer education. The intersection is a hard place to get into because they felt like they had a solution, right? So I'm going to take a step back and talk about Advance, right? Advance actually uses the same hardware that the V used, but it goes at the intersection and it solves a problem that was very difficult for traffic engineers to solve, and that's the dilemma zone problem. And so that gets us into the intersection where then we can introduce matrix. Because the problem with the dilemma zone is when you're doing it with loops, you might have two loops far back from the intersection that say, I detected it here and here. That means it was going this fast, right? Well, it was going that fast right then, right? But what if it's changing speed, right? What if it's changing lanes? What if it doesn't tell you if it's a large vehicle passing over that loop? And so having that detection only at that one point gives you something, right? But the Advance was head and shoulders above that by telling you all the way in continuously how fast that vehicle's going, how long it's going to take it to reach the intersection. And so that really allowed Wavetronix to jump into the intersection market with a big bang, right? Because it wasn't just cheaper, it wasn't just easier to install, it was a difference in kind, right? This was something that they simply couldn't do with the technology that existed at the time.
And couple that with a matrix and multiple zones where, again, you'd have to cut individual loops for every zone. It's configurable in software, right?
Correct. And so having that foot in the door with the Advance makes it possible then to develop what is an extremely complicated product with the matrix. It's got 16 antennas that are both transmitting and receiving at the same time, right? And so each of those antennas has to be fed with a big central switch that then goes out to 4 more switches, right? Because you got to go to 16 different channels, and you got to switch to each one individually. And then the algorithm to stitch all of those 16 things together and track the car as it goes through this antenna beam and then into the next antenna beam to figure out which zone it's in, which lane it's in, is a much more complicated problem than the HD had to solve. And I think the founders made the right call going into it, that we didn't have time to develop that complexity without any kind of revenue at the beginning of the company, right? And so once you've got the revenue, and once you've got the foot in the door with the advance, it suddenly makes sense to develop something at that level of complexity to really go into the intersections and make a big splash.
Yeah, and unless you're driving with James Eck, you won't know all this stuff. Like the average driver has no idea how complex an intersection can be and how much technology goes into this, right?
Oh, and I'm still learning every day, right? I know all about our products, right? But every time I have to interact with the actual cabinet interface, I realize they're doing a lot more in here than even I know about, right? The traffic controller is doing so much work. In the case of UDOT, at least, they've got complex algorithms going through all that data, figuring out exactly how well that intersection is performing and making those decisions. And there's just more than anyone, I think, could understand about the complexity of these problems.
Why do you geek out about it? Why does this interest you? Why is this your chosen field?
I always hated bad traffic. And so anger drives me, I guess. But when I found out what Wavetronix was doing in college, I said, you know what? I want to be a part of that, right? I want to make traffic flow better, right? I learned about the advance in particular and said that is making intersections a lot more efficient, right? Yeah, it makes it safer too. And we talk about safety a lot, but the efficiency that it adds is also was what really drew me, right? And so I still love advance, and it's getting old, but it's still one of the premier things out there doing what it does. And I don't know, traffic just gets worse and worse, right?
Yeah.
Traffic's never going to go away. And so it's, I don't know. I like to read a lot of heroic fantasy kind of books, right? And they say heroic things like rust never sleeps and neither do we, or evil never sleeps and neither do we. Well, traffic never sleeps and neither do we.
Yeah. Yeah. The Wavetronix sensors do not sleep. They're always working. So you say it's old, but it's tried and true. What's on the horizon for traffic detection and radar?
So like I said, with cars going into radar for collision detection and these things, it's getting a lot easier to go into radar, right? Like when Wavetronix came into the industry and disrupted the industry with cheap printed circuit boards with these parts on them, there's a lot of opportunity for anybody to come in and do the same thing with these new chipsets coming out. And so there's a lot of potential there, a lot of powerful processing that can be done to do things like what we've done with the XP21, right? Where the XP21 is using one of these chipsets, 5 copies of one of these chipsets to cover a whole intersection with just one unit, right? Because it's got the ability. Matrix, you had to have the 16 different antennas all pointing different directions. It can look over the space and calculate where things are in the space without having to switch from antenna to antenna, right? It can use Doppler to pick up the speed of things coming in and filter out all the background noise that isn't moving. And so there's just a lot of potential and power in these new chipsets to do a lot of very interesting things very, very cheaply. Yeah,
XP21, one sensor on a corner, and it's providing detection for all 4 approaches, right? So maybe as you're driving down the road and you're hitting all greens and you don't have that rage that we all feel when we have to wait at those red lights, what drove you to get into this industry? We can thank scientists who helped with World War II, right?
Yeah, all the way back.
Yeah, very cool.
To Volta and his pile of nickel and copper plates with wet rags in between, all the way back there. He had no idea what was coming.
Yeah. No, it'd be great for him to see this today, but we'll just talk about it instead. James, anything else you want to share with me that we haven't discussed?
No, I can't think of anything. Thank you so much, Todd.
You bet. Thank you. James Eck, our guru of radar at Wavetronix. Appreciate it. We'll see you next time on the Pulse Podcast.